there are things about it that are kind of high def, like, but something about that, I don't know, something about this just doesn't.
Versus like a Demon Souls or a Spider-Man or whatever. Yeah,
Yeah, right, right, totally.
not even close.
I don't know. This franchise does not seem good. Yeah. So clearly, fans did not take to that particular screenshot, or they took to it in exactly the wrong way.
Oh gosh, I can't imagine why.
They say, all publicity is good publicity, but this is bad publicity,
This
I'm gonna
is
say.
clearly very bad publicity.
Yes. Did you have a good holiday?
I had a really nice holiday. It was just long enough that I forgot what a Monday was like.
Yeah, I definitely have the holiday hangover right now.
It's worth it. It's absolutely worth it because that was a really nice 4-day weekend.
You're one of my few PlayStation Network friends. And so I saw you playing many different games this weekend.
Mostly Ghost of Tsushima.
Yeah. What was the other one that I saw you playing?
It might have been Skyrim.
Oh yeah, yeah, totally. It's Skyrim, and I was like, oh, throwback.
Yeah, it's cause my spouse is playing Skyrim.
Ah,
So it might have been me
yes.
signed in on the console, but I did make a character, but I only did it for like an hour, and then I remembered how extremely convoluted that game is.
Are are you a big Bethesda video game fan?
The best Bethesda was Fallout New Vegas, which they didn't make. So no.
Obsidian?
Yeah, it was Obsidian,
Yeah.
who is really really good at what they do.
The Elder Scrolls slash Fallout engine or whatever they do when you like talk to somebody and the camera like zooms in really close to their face.
God.
That one thing turned me off the entire series. That and their fetish for like decorating every room with like a billion pick upable objects that are also like physics objects. It's a very
Yeah.
strange fetish that they have.
When I was watching someone decorate a house, and I was like, this is impossible. And okay, here's the thing. I don't know if this was true on the PC, but on the console version, when you pick up an object to put it on a shelf, it's a physics object, and you pick it up from the very bottom of the object. So like if you were going to pick up a pot that was upright, you pick it up and it flips over and like is hanging upside down in your hand as you drag it to a shelf.
Got it.
But you can put
Got
it
it.
upright if you swing your cursor fast enough to make it physics upright, and then you drop it.
Oh, I see. So
It's
people are like, it's like that those toys where you have to like,
it's the old
there's
ice
like
cream
a
ice cream cone and the ball on a string.
yes, exactly, with
Yeah.
a string. Yeah. That's and for what? Why, like, I always wonder, like, why needlessly burden your game with not only the physics but the objects themselves? Like, why even put them there?
Yeah,
You know?
it's a level of, I feel like it's a strange level of role playing that like I really, there's parts of it where I'm like, man, this could really be like The Sims and that'd be great. Like I can see the want to build a house or decorate something, but like I do not care about every fucking wicker basket in every single dungeon. Like gosh.
Yeah, it's like the level design equivalent of the Uncanny Valley, right? It's like done with such a high degree of fidelity, but like with no attention to whether that fidelity is necessary or not, right?
Mhm. Yeah. Yeah, we'll
And
see.
it seems like it would make it annoying to actually find meaningful things, right?
And I feel like is that supposed to be the joke or the shtick behind it, where it's like you really have to be an observant adventurer? I don't know.
Yeah, I don't know.
We'll get to experience this anew whenever Elder Scrolls 6 comes out
Oh yeah,
in the next year or two.
yeah. I don't know. I bet Fallout 76 probably replicated some of that sensibility. I'm sure, but I'm not sure how many people actually played that game.
I didn't touch it. Yeah, though it is on Game Pass, right?
Oh,
But
okay.
but I don't have Game Pass anymore. So
Yeah, I canceled mine. I think I played like 10 minutes of like the remaster of Gears of War, and that was like the only game I played.
Gears of War just wasn't very good.
No, it's not very good.
I didn't like it. Yeah.
Yeah.
When there is a new Halo, I might like fire that up.
The
That's
Halo
worth
Halo
$10
got
a month to
panned,
me.
right? Like the new Halo, right?
The graphics were pretty bad for.
Yeah, yeah.
I don't quite understand what the Microsoft plan is right now.
Halo
But
Infinity, that's what it's called.
yeah. Oh, do you have it? Yeah.
I know it was like kind of jokey. One of the enemies, like the texture looked like it was from like 7 years ago with
Yeah.
PS3. What's the name of that bad guys? The orc looking dudes?
Oh, dude, I don't remember the names at all. Was it not a new enemy? Shit.
It was one of these guys, whatever they're called. But like in the level, yeah. Let me see if I can find something with less lens flare. I think it was this.
That's pretty rough.
Yeah, it's a little. I don't know.
I enjoy the image two to the left of that, which compares Beast Wars, the cartoon, to Halo Infinite. Up.
Which one? This one? Oh,
Yeah.
is Beast Wars? Was this the 3 or 4 elements? It was like wood, fire, earth.
No, that's Avatar. Beast Wars was like the Transformers animal spinoff.
Oh,
Where like
wait, this is a transformer?
that monkey is named Optimus Primal.
What?
That's the stupidest knowledge in my head, probably, but like it's great.
Oh, so you were like 10 years old when this was out.
Yeah, exactly.
You were like the prime demographic for this kind of thing.
Yeah. That was like my He-Man, probably.
Okay.
For a lot of
Yes.
us, for like a people 4 years older than me.
And it has this weird 3D animation, like proto 3D animation.
The entire show was 3D. It was cool as heck.
Yeah.
It's not
Probably
very
the
good.
animation was hand animated. There's no mocap back then, I'm assuming.
Oh, absolutely hand animated. Yeah, everything was like super jerky.
Super jerky.
Yeah. Oh man, Halo Infinite does not look good.
No, it doesn't look good.
Whoops.
I read some of the lore of Halo because I totally missed out on the Xbox generation, right? Like PS3 was like the first console I had since N64. There was
Nice.
like a weird gap in my time, right? And everything I read about Halo made it seem kind of ludicrous, but I guess that's every video game if you're not in Wisconsin. Like this person,
Oh yeah, the AI that lives in your head.
Cortana, right?
Yeah.
She seemed ridiculous. She seemed like a weird, like the whole game seems very chaste, and yet she was kind of like the male fantasy piece of it.
It's weird because there's not. Well, it's like a shooty game with no other humans in it, and they're like, we gotta make a sexy.
Is this
character.
a person or is he a robot? I could never quite tell.
His name is like John something. He's totally a guy.
He's totally a dude. Okay.
Yeah, who just gets frozen. He gets cryogenically frozen a lot, and then woken up when people need him. His armor is maybe magic, or he's magic. It's really unclear.
Oh, okay. So he's magic.
Yeah.
But he's also like high-tech cyborg guy.
Yeah,
He's magic.
Well, he's like the dude who got put in the super military suit. So he's like an army weapon, and everyone like salutes him because you are a Master Chief something something.
Master Chief, is that really that high up that everyone would salute you?
I think it's actually a civilian rank too, because isn't Chief not a military rank?
It's an enlisted rank and not a officer rank.
Okay.
Yeah.
I only know this because of Chief O'Brien.
Yes.
And Master Chief apparently.
Yeah. So Chief O'Brien would salute Master Chief because clearly, you would think that Master Chief is above regular Chief, right?
I think so. But is Petty Chief below regular Chief, or Petty Chief is probably also above regular Chief? I don't know what petty means, except bad.
Navy SEAL ranks. No, that's not what I'm
Okay.
interested in.
I mean, that's probably what it is, though.
Petty officer.
He's probably supposed to be a SEAL, or like a
There's
future SEAL.
Chief Petty.
Chief Petty.
Chief. I guess Star Trek has presumably Star Trek is like Navy ranks, right?
It's the Navy, yeah.
Warrant officer. That's kind of a mouthful.
do they
Chief
just-
Petty officer.
Do they just make up new
I'm
ranks when they
so
need to like
confused.
put a new level below them? It's like it's a pyramid scheme where they're just like, well, we've hired too many recruits.
What is
make a
Master
new-
Chief though? Is he Marine or is he like?
I mean, it's space, so I assume it's Navy. He must be.
Okay.
He must be a Navy dude.
He's in the Space Force.
Space Force. Oh, When Halo came out, that was just a twinkle in someone's eye. Can't believe it's real.
Let's bring it back. This does not look super awesome, right? This
Next generation.
there are things about it that are kind of high def, you know, like, but something about that, I don't know, something about this just doesn't.
Versus like a Demon Souls or a Spider-Man or whatever. Yeah,
Yeah, right, right, totally.
not even close.
I think they delayed this game. They delayed it for like a whole year,
I
which
think
is not
so.
never a good sign, right? A whole year is like, you know what? We're nowhere close to being done.
Yeah.
Yeah.
Speaking of too many things to pick up, though, I am looking forward to Cyberpunk.
Yeah, man.
I feel like
Oh, jeez, there's too much to do.
I was gonna say I'm gonna wait for the next gen version of that, but The Witcher had the same problem as Skyrim, where there's too much shit to pick up. But like everything in The Witcher was useful.
Yeah, yeah. You don't pick up like empty beer bottles in The Witcher.
No, it's
You can
food
only
and
sell the stuff.
ingredients and yeah, weapons.
Yeah. When you played Witcher, were you like a chemical Witcher? Did you do any of the potion stuff?
I did some of the potions, but it's kind of annoying.
I don't like things with ammo. Ammo always bothers me. I always use the infinite melee weapon in any game. You know,
That's
I just don't want to shoot my ammo.
that's fair. I just got so overpowered with the swords that it wasn't really a deal.
Yeah. Yeah, totally.
By the
I think I
way,
just used like the healing thing and
yeah,
that might have been it.
there was at least a couple potions like the night vision one was handy.
Well, okay.
There's a couple I used.
Yeah.
This guy is totally gonna be the cover screenshot for
This guy
for the
right
stream.
here.
Yeah,
Yeah, yeah, okay.
yeah.
Cool. I think this is actually the most famous screenshot from Halo Infinity before it got delayed.
Oh, that's rough.
So, Godspeed, whatever team is working on this now. I don't think
Yeah.
it's Bungie. I don't think it's Bungie anymore. They're
No,
fully on the Destiny train.
I mean, Bungie. It's some 343 studios or something. Bungie like bailed out of this 3 Halos ago.
Yeah, yeah, they just pulled the eject. Yeah. I don't know. This franchise does not seem good. Yeah. So clearly, fans did not take to that particular screenshot, or they took to it in exactly the wrong way.
Oh gosh, I can't imagine why.
You know, they say, you know, all publicity is good publicity, but this is bad publicity,
This
I'm gonna
is
say.
clearly very bad publicity.
Yes. Now here's
Oh,
us talking shit about somebody else's 3D graphics when you and I are just barely dipping our toes back into the pond of
I was to
3D.
say, put the square on the screen.
Yeah. So are we in development screen sharing mode right now, or is it
Oh yeah.
are we talking it's okay,
Oh
yeah.
gosh, no, the screen's been up for all of this because
Okay.
this is critical.
Yes, okay. You know. Um so maybe I think this session we were thinking it would be a good idea to actually not like what we could do is just like open up chronos.org and read the OpenGL reference manual together for 2 hours.
Mm-mm.
But story time is boring. I want to see pictures, right?
Yeah.
Um, and if we can't do pictures of cool stuff like actual graphics because we don't know what we're doing, maybe we can at least do pictures of the OpenGL state machine, which is I think something which always thwarts me whenever I learn or relearn OpenGL because I cannot remember. Am I setting a property on the object I just created, or am I setting a property in global state somewhere? When does that get overwritten? What else relies on that value? And some genius at WebGL2fundamentals.org, I believe it's the same person that owns WebGLfundamentals.org, went above and beyond and registered not one but two different domain names in order to teach us OpenGL. So yeah.
I was gonna say like not only I'm just so impressed by this interface because like not only is it like really cool, but also they went through the trouble of like all the little things are draggable and like everything about this piece of software that I've seen is above and beyond.
Yeah, I mean, they built an entire they built an entire like UI for this. I actually do wonder if this is like WebAssembly of some form or another, and they're just like importing a GUI library from externally.
I kind of assumed that it was all canvas, and that they're running the 3D in a tiny 3D context on top of it.
All right. Well,
Oh, we're
we're
about to
web
find out.
programmers
Yeah,
here.
yeah,
Yeah,
yeah.
we're gonna actually like take. This is not WebAssembly. This is totally friggin' stuff. Oh no, these are all scripts, right?
I don't
Let's
know what
see.
WebAssembly looks like. Yeah.
Certainly, no. This is just
Wow.
straight up like DOM that this guy document object model this guy built this in. Yeah.
Okay. I'm
Yeah.
impressed.
Yeah, cool. It's probably just React, you know. Well, let's see. There's class draggable. I bet this is React.
Yep.
Yeah. Well,
Interesting.
good for you. Good for you, dude.
Yeah.
So this is nice. It visualizes, I guess, individual objects that OpenGL will create and kind of keep around. It's got the canvas here is the actual screen.
Mm-hmm.
If I run this, this is the simplest possible sample program. I can't actually edit this thing here. It's just code, which is kind of a bummer. I sort of wish this was editable and we could paste our own code in here.
Oh, that'd be so
It'd be
amazing.
really cool, right?
Is this open source?
Are you proposing?
I mean,
Not all state is shown. Okay, well that's fine. That's fine.
there's a lot of state. No, I didn't even think to like we could just fork this and put our own program in there if we so desired.
Oh yeah, that's true. That's very true. Unless this is like painfully scripted so that every single thing has like a second piece of like metadata that like scripts the rest of this.
Yeah, that would be less interesting.
That would be yeah.
I don't want to do that.
Yeah. Very, very diplomatic way of saying that. It would seem easier, in fact, just to do an eval on this stuff, but then like every time there's an actual function call, have it do something over here, right?
Yeah.
In addition to actually modifying the canvas. So what this allows us to do, I reloaded the whole thing. The double arrow thing actually runs the entire JavaScript code to the end, but the single arrow lets us step line by line. And if I can somehow, I might need to zoom out a little bit more
I was just saying
because there's a window back there. There's a window hiding back here. Let me bump the font size up one more because I just think that it's going to be small. And I can go ahead and step through these. You were about to say, sorry, Dom.
Oh, I was gonna say something about your scroll bars being on. I think they could be off, but that's fixed too.
Oh yeah, I don't see scroll bars here.
They're,
Are you saying that I could turn them on in the operating system?
I think you could turn them off in the operating system because they were making the global state window that was what was showing up there being all hiding stuff. But
okay.
at this zoom level, it's okay. So I think we're fine.
Okay. So this example is a little bit uninteresting, so maybe we should do another one. Smallest GLSL. This is the one with the actual shader in it.
Yeah, and this one remarkably looks very similar to what we've already built when you run the whole thing.
So, oh my god, a lot of stuff happened. But
Yeah.
the thing to focus on is this square.
Also, holy shit, all the way things pop up in this is really mind-boggling.
Yeah, it's really cool. We had a magenta background and a white square. This person has a white background and an orange square. To each their own.
We'll get to this level. I believe in us. I think we could do it.
Yeah. Okay. So I actually think that like if we kind of talk through this, it actually sort of like there's not a huge amount that we can say about this particular program. I guess we can go over what the shader is. But I do like this. It's just like one story. One of the problems with the tutorials that we've seen online, they're actually like a little bit abstracted, right? Like that MDN one is a decent one, but they kind of like make a bunch of temporary variables and like store them in structures and like it's kind of.
It was really weird because the variable name changed every step of the way.
Okay.
In
So maybe it
just an
wasn't fantastic.
Unpredictable way, yeah. I'm glad we could follow it, but also, yeah.
So we can actually see what's going on with shaders in this particular example. Let me once again rearrange these windows. Okay, this is my one pet peeve here. I'm actually not sure what transform feedback actually is. So we'll learn. We'll learn together what that actually is. So I guess this is default blank slate OpenGL state. You got a bunch of global stuff over here. More than you ever need to know. Like we can unfold all this stuff. We can unfold stencils and there's this thing called a transform feedback floating around that's apparently replaceable, right? Because this is the default one. That's what it says in the title bar here. But this is just a pointer, which means that the global state points to some transform feedback object that of which there is one already created, but probably this pointer could be reassigned. Same thing with the vertex array. And actually, we sort of had an inkling about this, right? Because we had to do all these bindings for array buffers and that kind of thing.
Yeah, that was weird. I'm
Yeah.
hoping that in particular makes sense after this.
Yeah. So I will say that one of the things that this whole website does that we didn't do for our game or our example was they are doing what's called vertex array objects, whereas we kind of directly bound array buffers to the global state. They actually have something called a VAO, which I think just adds one layer of indirection to the whole game. I think you would basically bind a vertex array object to the global state, and that fills in this slot here. And this has a couple different things that you can kind of mess with. I think you can basically bind two more arrays to this thing, and we'll basically go through a couple different examples, and it'll make that clear what's going on.
Cool.
So the shader here, we've got a vertex shader. It has no input or output. It basically just has a position, which is the origin, and a notion of point size here, right? And I'm guessing point size is maybe just like a drawing primitive. This is actually something I haven't seen in OpenGL, but I guess they're just using one point that is 100 units in size.
Oh, I see. They are just drawing. Okay.
Yeah. Then you have your vertex shader here. I'm not exactly sure what this is doing because it's not really naming. Maybe it's saying
That
the
was
output of the output of the shader is a high precision float.
yeah. That was
But that's actually, but the output is actually a vec4. Yeah, the output is actually a vec4 for color.
that
So
was
I'm not really
that
sure
was
what this
just the
line is.
strange precision error that it asked for last time too. I think it's just something about WebGL 2 is really into that.
Yeah. You think maybe this is some kind of this seems like a botched variable declaration because I would assume it's like precision high HP float variable name, right?
Yeah, when nothing in here references
References it.
anything.
Yeah. Okay, so let's step through. First line, we kind of do some boilerplate where we pull the actual canvas out of the web browser context. In fact, WebGL is nice because it's actually the simplest possible way of doing this. Any other way of using OpenGL, you have to have some other library that taps into the underlying windowing system, one for Windows, one for Mac. There are some libraries like SDL and Allegro or other ones that like will abstract that away, but it's generally just kind of like a shitty time trying to get like your OS to talk to OpenGL. WebGL, not so. We just pull the context straight off the canvas.
Of all the OpenGL examples I've seen, like top to bottom, this is actually the shortest one.
Yeah, which is nice.
Yeah.
Okay, declare our shaders as just straight up strings. We'll notice they're actually doing this sort of prefix here, this preamble, which basically says which version of GLSL they're using. They're actually using a version that's more advanced than the one that we used, although it's available to us if we just add this sort of preamble. Right?
So that's actually being read. It's not just a comment for their sake.
Correct. It's a directive.
Okay.
These are C programmers, so the pound does not mean comment. It means some preprocessor or meta language feature.
Right. Cool.
Yeah. And we can see that like we didn't do this for our shader, right? Okay. We didn't declare an output. We actually just said GL underscore color, right? Was that what? And GL underscore color was some implicit global. But here we actually name the output. It's an output whose type is a vector4. It's a color, and then we assign that. And they're assigning it to just the color orange. So what's interesting about this example is really what's going on with the shader compilation, right? So we create a shader, and so the shader object is just created. It's not bound to anything yet. It's just kind of floating around.
I love this UI.
There's nothing in it, no source, right? But then we set the source on that shader. And this particular GL shader source function takes the shader that we operate on as an argument.
Okay.
So there, we've got the source in there, set to the string that we put up there. this if block here is kind of pointless, but basically it's just checking to see if it's um, already compiled.
Mm-hmm.
Oh no, we just compiled it, and it's just saying like, did the compilation succeed or not?
Yeah, just an error check.
Yeah.
Cool.
Now we create another shader. Let's make some space.
Can you close the transform feedback one? Do we need that, or is that just?
I can let's see. I can fold the varyings.
Interesting.
There.
Okay.
Yeah. Let's tuck that over there.
It's weird that it's always there.
Yeah. We're creating our fragment shader now. We compile it. So there's still just two compiled programs that are just floating around in nothing.
Mm-hmm.
And then we create an actual program. And so the program object, then again, is yet another object. And you can see in the lines coming up, we're actually going to attach the vertex and fragment shader to it. It's a little bit like a C or C++ linker, right? With the exception that you can't, like with C and C++, you can take an arbitrary number of module files and link them together. Whereas here, you get one vertex shader and one fragment shader in OpenGL, straight up. I think in other graphics APIs, you also have something known as a geometry shader. There's also ways of abstracting this stuff completely away and making it just programs that you throw onto the GPU to do things like physics or AI. But right now, everything that's being presented to us is under n layers of abstraction bundled up in OpenGL. And this is basically what, like whatever the capabilities that your graphics card has are totally abstracted away by that graphics card provider's OpenGL driver, basically. All right. So we attach the two shaders. It's nice because it has these two little like nodes, these arrows.
I love
that
it.
sort of, yeah.
Mm-hmm.
Say that there's a vertex shader and a fragment shader. And then we link the program. It says it's now linked.
What does link program do?
So link program says you're done. And it actually probably physically links the code together into a piece of executable code that the graphics card can run.
So we actually could have attached more shaders, correct?
Theoretically, although in the OpenGL parlance, I don't know if it's meaningful.
Okay.
Or even possible. Like, what happens if I were to it knew because vertex shader object here was created as a vertex shader, right? Mm-hmm. We said it's a vertex shader. If you try to attach two vertex shaders, I don't think it will know what to do with that because it has a slot for a vertex shader and it has a slot for a fragment shader. Oh, by the way, in Direct 3D, they call fragment shaders pixel shaders.
I've heard that before. Yeah.
Yeah.
Interesting.
I guess OpenGL people are a little bit more like it's Silicon Graphics, right? So they're old school graphics people, and they're like, no, it's not a pixel, it's a fragment. Because I think fragment is geometrically a little bit more sound.
Oh, interesting. Yeah. Okay.
Yeah. At any rate, I think the fact that it says vertex shader and the fact that it says fragment shader, it does correspond to the names of these objects, but it's not like OpenGL knows the names, right? OpenGL does not know the variable names in JavaScript. So I actually do think that this is saying you have a spot for a vertex shader and you have a spot for a fragment shader in a GLSL program.
Gotcha.
And you have to have both.
Okay. Cool.
All right. Some boilerplate about checking to see if it linked successfully, and otherwise, we actually have, now that this program is kind of orphaned and floating around, we actually need to connect it to the global state. So we have to use the program, and this is basically loads it.
Oh, I see. So actually, if we wanted to use more shaders, we'd switch programs. We'd draw something, switch program, draw something.
Yeah.
Cool.
And you're going to see that a lot, right? Essentially, what's going to happen in a really complex 3D program is you're going to be in a loop over a bunch of different models, surfaces, geometry, and they're all going to change what they do, right? Like even if you're going to draw my arm or like my hand, right? Like my fingernails would have a different shader than my skin, right? Yeah. So you would vary this program potentially hundreds or thousands of times per frame. Yeah.
Okay, cool.
Um, and as you can see, the program itself is also quite complex in that it's also got a bunch of like uniforms that you can change while you have that program loaded. You can essentially pass global variables in there. And then this program is also just it's actually an iterator callback, right? It like both the fragment shader and the vertex shader are essentially callbacks that are called once per vertex or once per fragment, depending on whether you're a fragment shader or vertex shader, right?
Cool.
So it's
Yeah.
almost like a map, like a we're doing a map over vertices or fragments. Yeah. All right, and then draw arrays is actually what's gonna basically plug our geometry, uh, which is nothing right now. We don't have any geometry. It's um,
Yeah, I noticed that the draw arrays call is actually its drawing points. The value we're giving it is 0, and we're saying this the third parameter is one number
yeah.
per
So
point.
let's see. Draw arrays. Is it draw array singular? Draw arrays.
Draw arrays.
First count. What's funny is that we're not actually using arrays. There's no array here because the shader doesn't reference it at all. The shader has no actual input, and the shader just knows what it's going to draw. So this vertex shader is essentially saying, I don't care what the input is. I'm just going to draw the thing that I specified. And then finally, voila,
Boom.
it is drawn. We've executed our program. We've iterated over exactly 0 points. And we've gotten ourselves a square.
Heck yeah.
Right.
That's so cool.
Yeah. Now, if we graduate in complexity, let's do the triangle, and let's actually see what the actual output is. See, this gets a little more complicated, right? We have this buffer here, there's positions, and this time we can't just tell our vertex shader, "Hey, draw a triangle," right? We actually have to specify that geometry in our JavaScript program, send it over to the OpenGL API, and then have the vertex shader know what to do with that stuff, right? So already, if we're looking at the source code, it's quite a bit longer as is, right?
But a lot of it's already looking similar too.
It's looking pretty similar.
Yeah.
All right, so our vertex shader is a little bit different. Rather than setting GL position to be something fixed, it is just taking a value as an input. So, like I said, your vertex shader is like a callback that maps over a bunch of vertices. Here we're declaring the type of input. Now, vertex shaders can actually have like lots of input. Like you can have lots of properties on a vertex, right? Last time when we were playing with this, we had colors on
That's right.
the vertices as well, right? Other things you could have is like a vertex normal. So you can basically tell the GPU essentially what angle does your vertex represent. And if you have an edge between two vertices, you can basically model almost like a smooth surface like that. And that's how you can get like kind of like very smoothly rendered spheres. Like you've probably seen like OpenGL spheres where they have like the little lens flare or the little like specular highlight on it.
Oh yes.
And they look really smooth, and they're not ray traced. They just have vertex normals that let you do the lighting correctly, right?
Right, and that's like the actual geometry is many fewer triangles.
Yes, exactly.
But the shader is handling that. Yeah, cool.
Exactly. So the shader can make and then you can have all kinds of textures, right? The most obvious form of a texture, and maybe we'll have time to actually do one of the examples that has a texture, right? Because there's like cubes with textures on them. The most common form of a texture is a diffuse texture, which all it does is like basically say like I'm specifying the color of the pixel that shows up on this piece of geometry, right? And generally that's always like the texture is a texture coordinate. So you imagine that the texture is like a decal sitting somewhere. It's just a graphics file, a PNG or whatever. And you're basically saying, if I drew a triangle over a piece of that decal, what would be the two-dimensional coordinates within the space of the decal that each of those vertices on the triangle corresponds to?
Oh, interesting.
Those two coordinates are referred to as U and V. U is the horizontal, like how far along the horizontal axis of the texture you want to go, and V is how far on the vertical axis.
I've seen
Um,
that. Okay.
yeah, and so you'll hear a lot about like UV operations. Like if you use a piece of like 3D software, there's like stuff that's about manipulating UVs and stuff like that. Yeah, and there's a lot of mathematical ink to be spilled about doing your texture interpolation in a perspective correct way, which we can kind of talk about as we get through this. Um, in fact, early video game consoles did not do perspective correct interpolation because it was actually it was like computationally difficult. So, like for example, PlayStation 1 does not do perspective correct texturing, and so therefore you get kind of like very weird looking graphics as a result.
That's so
Um,
interesting.
yeah. So what I was saying, where how we got here was we were talking about like a vertex shader doesn't have to have just one input. It doesn't just have to be the vertex. It can be a ton of properties. You can also have multiple textures, right? You can have the diffuse map, which is just like what color is being drawn on that piece of the triangle. You can also have a bump map, which you might have heard of before, or a height map, which allows you to basically apply textures and almost give a sense. The classic bump map I've seen is like a brick wall, right? Like a brick wall has colors. It has like the redness of the brick and the white kind of grout or the gray grout. But you can also have a height map that allows the lighting algorithm to kind of treat the grout slightly differently, and you can basically make imperfections and that kind of thing. All kinds of cool stuff, and you can also have multiple diffuse textures that are alpha blended together, right?
Interesting.
Yeah, and that's how you can get sort of random looking terrain with a very simple texture set, right? What you can do is just sort of arbitrarily overlap two or more diffuse maps that are alpha blended in a certain way. And basically the diffuse maps might themselves be simple, but the amount of combinations that you can have by shifting and translating them relative to each other gives you a lot of visual diversity, right? Because otherwise you just have maybe like a very boring, repeated looking terrain. Yeah.
You know, this is actually my take on Ghost of Tsushima. Because as far as I can tell, it's a geometrically very simple game that I think they've applied a lot of polish to visually. But like, I think that's why it loads so fast. Like, I think
it does load really fast, right? It's impressive.
It loads really, and it doesn't load faster on a PS5. It can't load. Apparently, just like is already at maximum speed.
Wow. Yeah, so it's just maybe not a high volume, or they just haven't optimized it yet. That's the other possibility.
Possibly, but like, yeah, I really feel like that thing is. It sort of feels like a low poly world that has been like extremely visually embellished.
Yeah, they have brilliant shader programmers. I guess at every AAA studio, but certainly at Sucker Punch, they just did such an amazing job. I played the shit out of Ghost of Tsushima over the holiday break. Although it was kind of past the point where I was having fun. It became the work phase of a video game. You know, like every video game is like 20 hours too long, and so it's like trying to get through it.
Yeah, I kind of wish. I wish I knew there wasn't a third chunk of the island coming up for me.
Right? Have you gotten to the end of the second act yet?
No, I'm halfway through the second act probably.
It's really long, right? You're ready for it to be done.
I'm ready for it to be done. Yeah, it's nice. It's nice that all the tales and the voice acting are actually like at least interesting, and I'm trying to avoid all the shitty side quests.
Yeah, I mean, the only reason to do side quests is to get supplies so you can upgrade your katana to the highest level so you can kill guys faster and therefore progress to the game faster.
That's true.
All right, so our vertex shader takes input. This one only takes one attribute, but you can actually plug a bunch of buffers, and basically we could map over a very, very heavyweight vertex. Like the vertex could have a ton of properties on it. Right now, this one only has position, right? Our fragment shader is uninteresting. It's no more complicated than it was last time.
Yep.
All right, so why don't we go ahead and just like plow through some of this shader setup. This is all the same as last time. We create and link our shader program.
Okay, this is where it's getting interesting. Yeah,
it's a fun thing that they're doing here. This is just to make things look visually good. You technically don't need the individual shader objects anymore after you've linked them into the program, because now they've been compiled into, like, imagine that you are compiling a C program, once you have the output artifact, you don't need the intermediate .os anymore, right?
Oh,
Um,
interesting.
nor do you need the .s files, right? Because technically a C programmer also like compiles down to, or really the first thing it does is compile down to assembly, and the assembler compiles it down to a .o file. Um, so it's basically saying we don't need these anymore because our program is whole, and that just declutters this particular website a little bit, you know.
That's so. What an interesting. Is there any advantage doing that in the real world?
No.
Okay.
In the comment here, they say, you know,
Yeah.
it is arguably not common. There's not really an advantage of doing that. I doubt the memory cost is particularly burdensome.
Cool.
Yeah. But maybe if you felt like your OpenGL was like really eating up a lot of memory, you might want to garbage collect those suckers.
So interesting. Okay. Cool. Yeah, I feel like compared to all the other stuff we're putting through the pipeline, like having any constant number of programs is probably not my issue.
Yeah. Yeah. So, well, it depends on how many shaders you have, right? Like you may have a ton of shaders. You may be dynamically generating your shaders on the fly, right? Like
That's what I can imagine.
yeah.
Yeah, if you're doing programmatically generated shaders, then you've got a problem.
Yeah. And that's where this kind of thing is helpful. Okay. So here is a pure JavaScript thing. You're going to see no changes in the OpenGL state. We're just grabbing the position of the.
Is it possible to scroll that up, by the way, or
Yes. Scroll this.
sorry, the other direction. Sorry, to put the position lock kind of in the middle of the screen.
Oh, yes.
Really, I'm just struggling where to put our faces on here because there's so much going on.
Oh, yeah. I'm sorry about that.
Nah, you know what? I'm gonna move us a little bit. We're gonna be a little smaller. We're just Windows in the OpenGL world now.
Oh, great.
Yeah.
I've been actually using on my side. I have us in the lower right corner of the OpenGL world. So
That's where we were. I just couldn't read stuff.
yeah, no problem.
Oh, of the world itself. Yeah.
Of the dark gray or the
Yes.
lighter gray background. Yeah.
That's where we are now. So the source code is
perfect.
visible. Yeah.
Okay, so what we did in JavaScript world, and I wish this would actually give us a little like, this is an awesome website, but I wish that position loc was now something I could hover over like an IDE and it will show me the value.
Yeah.
Because essentially what we did is we grabbed the index of the position, let's say like input variable, right? We defined position here.
Right.
Input variable, right?
And specifically, we're getting the attribute location out of the program. So it's a variable in the program that we are asking for a pointer to. Yeah.
Yes. And it's really an index. It's just like attribute, what index is this, is the attribute called position. It does a string search, it finds it, right? We could have declared uniforms in these programs too, and that's actually what we do in Manchester, or at least our 3D branch of Manchester, and we get the location of the uniforms, but we didn't actually declare any uniforms.
I think we actually stopped doing that. We
stopped doing that. Okay.
We did it on the first session, but took them out on the second one.
Okay, great. The uniforms will come back into play. Oftentimes what you see with uniforms is stuff that is global across all geometry. So that's things like the view matrix and the perspective matrix. It's like where's the camera in the world, right? The camera typically doesn't change across different objects that you're trying to render. The camera's position and its perspective is the same. Yeah. Other uniforms is something like global lighting, right? If there's one light in the whole world, that's not going to change across your geometry either, right?
Gotcha. Cool.
Okay, so we are going to create a vertex array. Now, there's actually a vertex array that's there by default in OpenGL state, according to this website. I think we're going to blow this one. We're going to be blowing that away. So we're going to create a vertex array. See this one?
Boom.
This one's called triangle VAW. These names aren't in OpenGL. Those are just the JavaScript names. And then we're going to call bind vertex array. And all that really does is it puts the vertex array on the workbench, because there's going to be functions in the future that say, I need to operate on a vertex array. Which one should I be working on? Because like we can just call create vertex array like 1,000 times, and we just have 1,000 of these windows floating around. But we need to know, for the purposes of subsequent OpenGL functions, which one of those things we're going to actually be manipulating, right? So if I move ahead, I think this one in the background is just going to go away. The default one, oh no, it doesn't go away. It actually is just there
It's hanging out, yeah.
hanging out because I think what happens is if we can also call unbind probably or bind null. I think it's bind null,
And you get the default
and then
again?
we get the default one back, right?
Gotcha.
And this is why in Manchester we didn't actually create a VAO. I think there was just a default VAO that was there.
I
We
thought
never called. I don't think we ever called create via vertex array.
Oh, I thought we did because we discovered that our binding was weird. There was one context where we weren't binding it when we needed to.
Interesting. You know what?
Oh boy, are you doing some Rust?
I am doing Rust. Yeah, Advent of Code starts tonight.
Oh, delightful.
Yeah, it's gonna be fun. And I'm gonna try to do it in Rust. I did it in Rust last year. Barely limped through it. Um, 3D was that what it's called? Canvas 3D renderer. Yeah, so we just bind the buffer straight up. We don't have we didn't create a vertex array.
Wait, oh, I see. We created the
Yeah.
buffer.
Yeah, and so
Okay.
I think earlier on I said, this happens to explicitly create the vertex array. But what's nice about this website here, what's nice about the diagram is it's kind of explaining to us that where did my window go?
Different desktop?
Oh yeah, different desktop. Oh, you know what? It's my full screen desktop. That's why I'm so distracted.
Mm.
It's in the fourth screen in my series of screens. The idea that there's this default one here is a nice abstraction that this website's giving us because it's basically saying, by the way, there's this one that's there by default.
I see. So Manchester, we did not create a vertex array. We created a buffer that we bound to the default vertex array.
Correct.
Cool.
So the question that should actually come into our minds is, well, why would you want to create multiple of these, right? If there's one there by default, like why make our own?
I do have that question.
Yeah, and we can talk about that in a second. Yeah. Okay. So we create a vertex array, and we're gonna bind stuff to this. So not only have we put the vertex array on our desk, we're gonna also talk about which vertex array we're modifying, right?
Mm-hmm.
Okay, so now we actually have some geometry. This is the first kind of instance of sort of geometry from the external program, the actual game executable or whatever, feeding it into the graphics program, our shaders, right? So we created a float32 array. It looks like this particular array's format is just 2D vectors, X and Y coordinates. These X and Y coordinates are in screen space because I don't think any of these shaders do any kind of transformation, right?
Mm-hmm.
They're not like projecting or anything like that.
Yep, correct.
And we saw from before that these can actually be quite complicated, right? We could make it 3-dimensional vectors if we wanted to. And the API actually provides us the flexibility of doing that because we just tell the API exactly what format we're passing into it, right? So let's move ahead. This thing is just so far just a JavaScript array,
Yep.
plain old data. But we're going to actually make it into an OpenGL construct. So we create a new buffer. All right, a new window pops up. We bind the buffer, and this is putting the buffer onto the desk because future functions are going to manipulate it, right? And we put it in a position on the desk called the array buffer, right? So there's no arrow here pointing to this window yet, but if I go ahead, then an arrow starts pointing there. So this array buffer binding is like a specific location on the workbench that is OpenGL global state. And then we're going to use that in future functions to manipulate it. In fact, this next function that hasn't run yet is exactly going to do that, right? It's going to basically say, let's take that array of stuff in JavaScript land that we just created and move it over into OpenGL land, right? So we're going to take that and say that the data for whatever buffer is sitting at the location for the array buffer in the global state is where that data is going to go. So when I click this, suddenly we've essentially mem copied all that data over.
Boom. Looks good.
Yep. And to be super painfully clear, and I think it's obvious basically what's based on the visual here, if we manipulate this array in JavaScript, it does not affect this anymore.
Right.
Very few things, in fact, probably 0 things, are pointers between OpenGL state and, let's say, user code state, right? Very few. I actually think probably nothing. So everything is just being like copied over. We're essentially just like populating a giant data structure inside OpenGL state that has nothing to do with user code. All right.
Cool.
Okay, so now we are going to call enable vertex attribute array. And I don't even know where that's going to happen. So if I click this, oh, cool. So it basically did it in the vertex array object. That's what VAO stands for.
What?
And yeah, sorry, go ahead.
No, what is, so enable position lock. What's happening here?
Yeah. So what we've said is that, like, you know how I said that a vertex can have a bunch of data in it?
Mm-hmm.
What I've said is that, what I actually meant is that it has a bunch of different attributes. One of the attributes is position.
Mm-hmm.
One of the attributes is color. One of the attributes is normal. All of these attributes actually, in the version of OpenGL that we're using right now, have no semantics around them. They can be whatever you want because the shader defines what the behavior is, right? The shader says, I want to use attribute 5 as the position, then it'll be attribute 5. In this program, it's attribute 0 as the position, right?
Mm-hmm.
It's pretty arbitrary. And we can also have coordinates for a diffuse map. We can have coordinates for another diffuse map. We can have coordinates for a bump map or a height map or whatever. Like there's all these, and those attributes can be basically used for arbitrary things.
Gotcha. Okay, cool.
Yeah. I actually think that probably the first versions of like physics simulations on GPUs or even like Bitcoin mining or what have you, they probably use the friggin' OpenGL API and like essentially expressed everything in terms of all of these primitives as if it was graphics, but it's not. It's just like a bunch of ones and zeros.
That's so wild. Yeah.
The analogy that comes to mind for me when I say that out loud is like, do you know how JPEGs are actually just like Fourier transforms? They're like, it's like a bunch of like coefficients of sine and cosine.
Oh, really? I did not know that.
Yeah, so they basically treat the image as a signal, like signal processing signal that's just like one long bit string.
Oh, how interesting.
Yeah, and so it's almost analogous to a sound file. And they run the similar type compression that you run over like an MP3 or something like that.
Wow. Oh, that's clever.
Over the image data. Yeah. Okay. So next is this mysterious vertex attribute pointer call, and this is going to do it's going to do like a shit ton of heavy lifting for us here. It's basically going to say, hey, that buffer that we declared here, or rather, it's actually not. Does it actually do anything with the buffer yet?
I don't think so. I think it's telling the position lock attribute in the vertex array object.
Yes.
How to use the buffer.
Yes, exactly. So it's saying like we are going to be putting something here.
Yeah.
But we're going to tell you what format it is, right?
Mm-hmm.
So when we go through that, we've done a lot of stuff here, right? And what's funny is it actually has bounded. So
what part of that bound the position buffer is what I don't understand.
Yeah, so I think what it is that it takes whatever is in array buffer binding.
Okay.
And then binds it to the buffer for whatever attribute we've enabled.
Okay.
Right. So if we enabled a different attribute and then called vertex attribute pointer, it would take whatever buffer is currently in array buffer binding and point it at that.
Interesting.
Yeah.
Okay. And we had to write both of these. We used both of those functions in ours, so that makes sense.
That's correct. One of the things that kind of gets me is that like this thing, I suppose there may be situations where you want to like maybe configure this, but flip it on and off dynamically. That's the only reason why I could imagine you wanting this to be a separate function from vertex attribute pointer, right? Because like looking at this program, they seem kind of redundant to each other, right?
Yep. But I assume there's a complementary disable vertex attribute array.
Yeah, yeah. It almost feels as if we would have wanted to like tell vertex attribute pointer what buffer we were passing in there, but maybe OpenGL doesn't actually have a way of indexing that. They literally only have this one slot up here in the corner, right? That's just like, that's the thing that we're currently working on. And I don't know how to close that window. That's the thing that we're currently working on. And when you call vertex attribute pointer, you're telling me the format of the thing that's sitting there on the desk. And then I'm going to point that attribute at it, right? Okay. So far, so good?
So far, so good. It remains
All right, so now we're gonna,
mind-boggling, but I get it.
Yeah, so now we're going to draw. And so we use the program and then we draw. This use program could have gone anywhere that the program was actually available. It doesn't matter that
it could have been before they detached the shaders.
Yeah. And then we're going to call draw triangles.
Wait, sorry,
triangles.
Use program just linked a lot of stuff. Oh.
Use program just did this, right?
It also connected the attribute to the vertex array object.
Oh, interesting. Yes, very cool. Yeah, yeah.
That seems like it's an implicit connection based on this.
Yes. It seems, I think maybe that's what the dotted line means, is that like it's not actually setting any state. It just happens to be the case that this is the vertex array object that is currently loaded.
Mm-hmm.
This is the shader that's currently loaded. And when this program says, hey, I need something for attribute 0, the vertex array object can furnish that, right? That's why I think the dotted line here is, I think you're exactly right. It's
gotcha.
Yeah. All right. So when we call draw arrays, we still actually, nothing in this vertex array object has told us, it has told us like, we have a bunch of pairs of floating point numbers. But I don't actually know what those pairs of floating point numbers represents. They could be points that we can connect as a line, right?
Mm-hmm.
They could be points that we don't connect at all and draw as individual pixels, which is actually what we did with the first example, right?
Right.
But instead, we're drawing them as triangles, which means that every group of three pairs of numbers represents a vertex on a triangle. This is what is known as the primitive. This is like, which primitive are you drawing? Are you drawing points, lines, triangles? There were a couple other primitives that we toyed with last time. We toyed with the primitive of a triangle strip,
yep,
and a triangle fan.
Mm-hmm.
And that's just basically how do we these attributes tell us, this attribute pointer function told us where are our vertices, and then this primitive indicator tells us what do those vertices mean? What do you want me to do with those vertices, right? Okay, so we're basically saying this array, this buffer could have way more geometry than we actually want to draw right now,
mm-hmm,
right? And we're just basically saying of the stuff that's in that buffer, we want to start at the 0th position and draw 3 of them, right? Cool. So let's draw it. That's satisfying.
Boom.
We had talked a little bit before about why would we want to create more than one of these things, right? If we had a default one here, why would there be multiple VAOs?
Yeah.
And it's because you may want to prepare a bunch of these things and then switch between them as you draw stuff. And that will save you the time of having to like create buffers. And so what a lot of programs will do is they'll create all the buffers they need up front. They create all the VAOs that they need up front,
mm-hmm,
all the various attributes, and then stick them in a JavaScript level index somewhere, like a database of these things. These are probably just different models. And then maybe even associate those with particular shaders that you want, and then iterate over that giant data structure,
gotcha,
and then call use program and draw arrays on those.
You've fed the GPU all the data you need, and if you're in memory, you're probably fine in terms of loading. And actually,
yes,
like, there probably isn't dynamic loading. You're probably like pausing, going to a loading screen, and loading more data and programs up in advance instead of dynamically dropping like one of these in
That's right.
as you need it. Okay.
Yeah, and whether or not those buffers are actually in the GPU or if they're being like streamed in by OpenGL,
Right.
I don't know if OpenGL necessarily wants you to worry about that. Like, you probably do need to worry about that from a performance perspective. But I think at the highest level of abstraction, it kind of pretends that there isn't a GPU there. But certainly under the hood, it's probably moving all that vertex memory into the GPU. And so potentially what's going on when you're waiting for your game to load on the load screen, it might not simply be waiting for stuff to come off the hard drive into RAM. It may also be doing a bunch of this shit, right? It may be doing a bunch of like bind buffer,
That makes
create
sense.
buffer, kind of create VAO stuff.
Hmm.
And basically setting up a bunch of state ahead of time so we could rapidly change between those things when we want to actually render the scene. Right.
Cool.
All right. Should we talk a bit about the more complicated one? We could go to rainbow triangle, and this really the only difference between this and the previous one is that we have more than one attribute per vertex, right? We talked a little bit about having
Mm-hmm.
we talked a little bit about having more than one attribute, and I
That's
gave you a
right.
bunch of examples. And so now we actually have a diffuse. No, we don't. We actually just have a color, a diffuse color.
Now, how did Manchester handle this? Because we did set color on the last one.
Yes, we did. So we did the exact same thing in this as we did on this example.
Oh, we bound a new buffer to an attribute, called it a day.
Yeah.
Yep,
So
you're totally right.
our shader had two attributes, a
Hmm.
position and a color.
Gotcha. Okay.
Right. I don't, we had a V coloring that we're using the earlier version of OpenGL, so this is not labeled with the word out. This is a lot clearer what it means, right?
Yep.
Yeah. So in this version 3, I think this is 3.0. It's not version 300. I think it's 3.0 of GLSL, or OpenGL ES, really. It's confusing because not only is there a version of OpenGL, but there's also the version of the shader language. ES means embedded system, so it's what we're using for WebGL. It's what you'd also use on like a PS3 or PS4.
Oh, interesting.
Yeah. We now have two attributes, a position and a color, and we now have one additional output. So what we're seeing here is that you don't have to label the output for the position, which is funny because the fragment shader, you do have to label the output for the color. I would have thought that the fragment shader's default output would be color.
Well, it's using the GL position special name here.
Yeah, exactly.
That's like a keyword assignment. Yeah.
Yeah. I think maybe probably in this version of GLSL, they found uses for fragment shaders that weren't just emitting colors. So maybe it emits other things besides colors that you want, right?
Gotcha.
Yeah.
Okay, then this looks very similar to ours.
It looks very similar. And so what you're going to actually see here is probably pretty much something that's really similar to what we just stepped through last time, except that we have two attributes. So you can imagine that we're going to have to bind a new buffer with different properties. And that actual buffer actually has a different structure, right? One buffer is... we'll actually see what they're doing here.
One buffer is going to be
positions,
two value points, and one is going to be 3 value colors.
Exactly, which is similar to what we had before, right? So everything up to here is almost exactly the same, except that on this line of code, I don't know if you can see it over there.
I can, yeah.
We're pulling out the attribute location in the shader for the color input.
Nice.
Right? Create our new VAO here. This is probably, strictly speaking, unnecessary for this program because, again, there's a default VAO. They're just trying to make the point that you can create a bunch of these things, right? We go ahead and bind our position. This is all still the same. And now this is the new code, right? We actually have a new array. And it's interesting because it's an array of not floats, but bytes, unsigned integers,
Hmm.
right? But then there are actually way more of them. There are 12 elements in this, whereas there are only 6 before, right? Um, and so when we actually, everything else is the same. And notice that we've actually, I wish I didn't go so quickly because I moved the pointer from the position buffer to the color buffer. We've
Right.
actually changed, we've actually like taken the position buffer off the table and we've put the color buffer on the table, right?
Right. Yeah. The array buffer binding global state is what's updating. That's
Yeah.
I really like seeing all these globals like updating in real time.
So what's a little bit confusing though is that array buffer is not the only place on the table that we've got. You notice
Yep.
that there's a vertex array. Sorry, there's a uh,
I mean,
I feel like there's another one,
okay,
but
because it does look like the only place we got right now.
maybe it's the only place. Yeah. Um, yeah. So let's go ahead and power through. One thing that this VAO doesn't use yet is an index array,
Mm.
which is interesting. And we can talk about an index array in a second. Um, uh, so what we're doing now is, okay, we actually created the 2 buffers first. So they're doing things kind of like in a breadth first style. That's like, let's create all our buffers first. Then let's set up the VAO with each of those
Well,
buffers.
and this particular line that you're on right now is actually what was throwing me on the last one is that you have to bind the buffer before you set the vertex at your pointer,
Yeah,
which
exactly.
was also our problem the first time through
It
as
was
well.
confusing, but it's basically because vertex attribute pointer essentially binds the VAO's attribute
To the current array
to the
buffer.
buffer.
Yeah.
Yeah, exactly. All right, so that's familiar. And now we move to the second attribute. We
Hmm.
enable it. We've also got the other buffer
Yep. Still attached.
bound to the global array buffer right now. And the parameters here are totally different. We're saying that each element is an unsigned byte, but there's 4 of them per vertex.
Hmm.
Right.
It also says do normalize, which is interesting.
Yeah. So I'm assuming there's just like a bunch of extra options that we can do, and there's also a stride as well, which basically a stride normally says like how many things should we skip, or like maybe it might even be possible to interleave. It might even be possible to interleave the
Oh,
positions
colors
and
and
colors into the
oh,
same
that's
linear
cool.
array, right? And you notice that the stride and offset would allow us to do that.
Yep.
What you're basically saying is that like, what if we did want to interleave these and we did like 2 positions, we had two floats for the position and then 4 floats for the colors.
Hmm?
We could say that the stride is what, 6? It's like to get to the next vertex, you need to jump six items,
Oh, and the offset is 2 because you'll
and the
go
offset would
2
be
and
2 for the color, right? Something.
fascinating.
Yeah, I think that's what this is for.
Cool.
It's allowing you to be very, very flexible in how you use your memory.
Hmm.
Because maybe in an embedded system, you don't have the luxury of just like keeping these 2 things separate. Or maybe you're reading them off disk in a packed interleave format or something like that.
Yep,
I'm
that makes
totally
sense.
speculating here. I don't have direct experience working with something like that, but it seems like the API will let you do something like that.
Yeah, well, and all of that has. I feel like in my mind, I can imagine why you do all those things. So
Yeah. Yeah.
seems good.
Great. And now we just draw the triangles. Again, this is all the same, but this time the shader cares about 2 different things. But since we've bound the VAO, the current VAO, to this thing, and that has the 2 attributes ready to go, essentially what's going to happen is the shader is just going to iterate over every vertex in this VAO, right? And each vertex has a bunch of different values bound to it.
Cool.
Right? 2 for the position, 4 for the color, right? And then we get our thing.
Boom. Sweet. Also makes
Yep.
sense.
And
Excellent.
then I think the final comment here is like, we only specified 3 different colors here. Why do we see a gradient? And the reason why is that our fragment shader is not simply being fed V color from the vertices. It is being fed the interpolated position and interpolated color for every single fragment / pixel in the whole surface, right? So it'll basically say, I want you to give me what's called the barycentric blend uh, between the value in vertex 1, vertex 2, and vertex 3. And it's basically a weighted average, right? Give me the weighted average of like how far am I from vertex 1, how far am I from vertex 2, how far am I from vertex 3. Make those weights all add up to 1, and then basically use those as coefficients to multiply by the attribute value in vertex 1 times the same attributes value in vertex 2 times the same attributes value in vertex 3.
Now, is that configurable, or is this just a behavior that you can't change?
That is a really good question. It is only configurable, as far as I know, by doing perspective correct versions or non-perspective correct versions. And I believe to do perspective correctness, that's the default. But if you don't want it to be perspective correct, you add another qualifier in front of the variable name.
Okay.
Um, and I don't remember what that is. But you're right to say that that is a very weird behavior, right? Let's just like interpolate between them.
Well, and I guess to me it seems wasteful if I'm drawing a triangle of a single color. Why? Why should I
Why
have?
even interpolate?
Why? Yeah. Why do math?
Yeah. So that's a good question. I think that's just the way. I don't necessarily think that's like necessarily what has to happen, but generally speaking, I even think the hardware these days, that piece, like the gap between the vertex shader and the fragment shader, the reason why you have these conventions is that it turns out that like doing that interpolation or rasterization is kind of the technical name. It's like, how do I convert this geometry, these triangles of 3 points, into individual like a rasterized version of that, individual pixels or fragments? That turns out to be something that you want a custom piece of hardware to do.
Okay.
So it's kind of hard coded at that point. It's not. I bet that there are renderers out there or GPUs out there that allow you to configure that kind of thing.
But this is actually like baked in at the low level. Like
Yes.
as you feed pixels through the GPU, it's just doing it, and it don't care. Okay.
In fact, triangle rasterization was the very first thing that any accelerated graphics card did. Before you could do vertex shaders or fragment shaders, really expensive thing was saying, I've got these 3 pixels, I want to treat them as a triangle, and I need to interpolate some shit over it. That was like the very first thing that they wanted to accelerate. Yeah.
Cool. Okay.
Yeah, but it's kind of weird because it seems very, very fixed to a particular type of application. And it also seems like, how would I use my GPU in a more generic way? And it turns out that they have other ways of getting around that. But this pattern is so common that it's just the way that everybody expects it to happen, right? And it's going to get even more specific and weird, let me tell you, because there's also what's known as, like I said, it respects perspective, right? Like the
Yeah,
when
that's
I
gonna
say
mess with me.
yeah, it's going to mess with you because like perspective correct. Let me see if I can find perspective correct, a good image of this perspective correct interpolation. And there's a very, very good image that you always see. This one's good. This one's pretty good.
What
Let
the
me see here.
fuck?
Oh yes, this is great. This is the drawing I was looking for. So imagine that your texture is like a checkerboard, right? If you just show the texture like flush with the screen, it would just look like it's a regular checkerboard. But this triangle here, you can imagine that this sort of blue corner is like further back. It's kind of angled away from you. You know, this side is closer to you. This side is further, and the way the texture is being drawn implies that, right? But if your texture is if your render is not doing a perspective correct interpolation on the texture, it's just going to draw it as if every point on the triangle was at the same distance away from the viewer.
Weird. Okay.
Right? And so if you think about it, doing this kind of stretching stuff is actually kind of hard. You kind of not only have you kind of have to like figure out how far back every single pixel is away from the camera in order to figure out like where on the texture you actually want to be reading from to draw the color.
That's so interesting. Okay, so that makes sense why
Yeah,
it's extremely efficient at doing interpolation between these 3 points. Because to do any texture at all, you have to do the exact same operation into like a JPEG or a PNG instead.
exactly. Exactly.
Ah, okay.
Yeah.
Fuck. That's weird.
It's pretty weird, right? It's very weird. And
But it's clever.
like I said, PS1 couldn't do this. So essentially, when you had textures in PS1, you either had to fake it or everything just kind of looked like this.
Wait, can you show me an example of a PS1 incorrect texture?
What if I wanted PS1 style game arts? Do they have? Yeah, so there's this guy here.
Okay. Interesting. Was
I'm
it
guessing. I wonder if N64 did it. It was actually. Oh, this is actually worse than the real PS1. Um, there's a guy. It's not Fabian Giesen. There's this guy who does this like break. He does like source code reviews, um, of like Fabian Sanglard. I get him and Fabian Giesen confused because they're both two like Fabians who do graphics. But he has a really cool breakdown of PSX. Is that what PlayStation 1 was called?
sometimes, yeah. I don't know why.
Lack of perspective correct texture mapping. Um, so this is a perspective correct texturing, and this is affine is basically what it could do. So you notice that it's not quite foreshortening the texture the way that you expect. It is sort of like skewing it. It can do the skewing, which it can do, which is easier, right? You just have to interpolate in 2 dimensions, but you don't have to account for the z value, right?
Oh, so it must look really strange when you're moving around.
Yeah. Or it just
Whoa.
looked like the late 90s, you know?
Right, the 3D was a little off. Okay.
Yeah. You see how, this is like skewed and like these lines don't look straight in your brain,
Yep.
and
Yep. Oh,
yeah.
fascinating.
Yeah. And this is the difference between having your hardware do it for you and having to not, like a lot of software rasterizers. You can write OpenGL implementation purely in software, but this is at least one of the pieces that's extremely expensive to do in software.
Well, I remember that was one of the big tricks with Doom, right? It was totally software 3D, and it was mind-blowing at the time.
Yeah.
But I guess actually putting it on the PlayStation or the N64 necessitated them actually writing it in 3D. That's funny.
Yeah. Doom and Wolfenstein, that era of 3D games and even prior to that, those were kind of amazing because you couldn't really fully represent the 3-dimensional world. We have a certain loss of granularity even in this realm of just like polygons, right? Let's draw a bunch of surfaces with triangles. Like I think we're used to it by now because we've just been like living in that world, but that's part of the language that's kind of it's in the marketing of when we buy hardware and that kind of thing. So we kind of say, okay, that's normal, but it is like a pretty piss poor representation of what things actually are, right? And they actually had to use an even less precise modeling of the world for something like Doom or Wolfenstein, where you couldn't even look up or down, right? They assume that all the walls are a uniform distance from you, from like the ground all the way to the top.
That's so weird.
With maybe some gaps, right? Maybe some gaps, but like, yeah, you couldn't really have too much inconsistency with it. I think Quake was one of the first games to just like say like, okay, we're gonna fully model the world and be able to look around in a bunch of different ways.
Right, Quake was the first game that had mouse look, I think.
Yeah. Did you ever play Descent?
Oh yeah, that's a whole different ball of wax.
That had 6 degrees of freedom as well.
That was
that you could kind of look up and look down. I don't know how they did it.
I think this was also real 3D.
Yeah, you can. Yeah, so they got these slanted ceilings and that kind of thing. You couldn't do this, and I don't think you could quite do this in Wolfenstein.
No, not at all. Yeah.
Yeah, certainly in Doom, you could not have like a roof and then something below the roof, right? Like I don't think you could do that. Yeah. Sweet.
Okay, cool. Thanks for answering that weird question.
All right. Well, that's actually not a bad sort of segue into the cube
I say
thing.
take
So
us
the
to Cube Town.
Cube Town has a lot of stuff going
Holy
on
shit.
here, right? Did I?
Did it
Oh, I had
crash?
to. Oh, it has breakpoints or something like that.
What? Okay.
So Cube Town is crazy. Is there a draw single cube?
No.
Okay.
But at least the drawing is like it's draw 3 cubes at the end.
Yeah. So there's a lot to talk about here. What time are we at right now? 8:30? Okay, so we have about half an hour left. I think this is pretty much gonna close us out here because we got
Oh,
a
yeah.
lot to talk about on this one. We may or may not do perspective graphics in Manchester. I've been thinking about it a lot, and like it would be cool to do one of those. It would be cool to do like Super Mario Galaxy, where like you could see the horizon and the world kind of like rolls in from underneath you. Kind
Oh
of.
shit, that would be cool.
And that you can't really do with isometric, right? The other thing about isometric is like the information density of an isometric display is not very big because there's no foreshortening. Naturally, you can't
Right.
show like stuff that's farther away from you, and that may or may not be fine for the game that we're trying to make.
Oh, but I
Um,
I love the vision you just articulated. So
okay, yeah, I do too.
that's aesthetically very cool.
What's the company? Uplink Game.
Oh man, I beta tested this
You did.
way back when. Yeah.
What are they called? Introversion. They made a
Yeah.
game. Uplink was rad. It was a really good game.
It was super freaking good.
But
Yeah.
they made Darwinia.
And they pivoted into Prison Architect. Damn.
Yeah. And they kind of did the aesthetic that we're going for a little bit, where it was our real-time strategy game.
This game was cool.
It was fun, right? I think it was kind of this was like basically Warcraft, right? Or a little bit like more large scale because you had little guys to run around.
It was kind of like Pikmin Warcraft. Yeah.
Yeah, yeah, exactly.
Uplink was cooler, but this is really sick.
But this is what we're talking about here, right? You kind of have the whole horizon,
Oh, I
and
like
you can
that.
kind of move around. Yeah. What's another game I'm thinking of? Scorched Earth 3D. I love Scorched Earth 2D, and Scorched Earth 3D was actually pretty good.
I don't think I ever played this.
Scorched Earth 1 was an artillery game. You have a bunch of tanks, and you set
Oh,
the
that's
power
right.
and angle, and you had like destructible terrain,
Yeah,
right?
yeah, it was like a little Worms clone. Yeah.
Yes, exactly. I think it precedes Worms by quite a bit.
Interesting. Okay, so Worms is a Scorched Earth clone.
Yeah.
Fair. That does make sense. Oh, cool.
Yeah. So Scorched Earth 3D was the same thing, but you could also rotate, right? Like it's like Worm. I don't know if Worms ever got 3D, but
I don't think so. Oh,
this
is
also
cool.
has. I mean, the horizon's not too far away. It's actually far enough away that it's flat. It's not. This isn't quite Super Mario Galaxy, right? But yeah, this was a fun game. You could kind of just like destroy the terrain and that kind of thing.
I really like that.
I
Yeah.
believe this was also fully open source too, which is incredible.
Neat.
But yeah, that was a little bit of a rabbit hole because we were talking about like, are we going to actually do perspective in Manchester? But we could. It might be fun.
I could. Yeah, I think I was into isometric, but I love the idea of doing like the game on a tiny sphere, a relatively tiny sphere.
Yes, and we could get you can fit more with perspective. Yeah, and as we'll see, the graphics pipeline is kind of like hard coded to support perspective projection, anyways.
Interesting.
So
Is it a huge pain to actually do?
isometric?
Isometric,
I don't
yeah.
think so. What's interesting is I was working through my textbook for 3D graphics.
Nice.
Not working through it. What is it called? Like 3D math. for games, or it's essential math for 3D games, uh, for games and interactive applications. Yeah, this is my book. It was not. This is more money than I spent on it when I bought it 11 years ago. Something about textbooks nowadays, right?
Dude, we're just ripping off students. That's our entire raison d'etre
Right,
as a
right.
society.
It's just all of like student debt. That's is basically artificially inflating these numbers, right? Abolish debt.
Yeah,
Um,
we're gonna get a whole $50 back from Biden when he's done.
shit. Um, Van Werth and Bishop. This is a pretty good book. I've cooled off on it actually because like reading it in retrospect, these guys are a little bit too good at math for them to remember what it was like to learn math in the first place.
Mm-hmm.
Um, but it's also not the most like if you have like a 4-year engineering degree, then I think this is a tractable book. But if you're just trying to pick this stuff up from the basics, I don't know what you do to learn at this point. I think it's probably better to just kind of like learn through application. But we were working through this book, and it didn't even have a section on isometric projection. But we can figure that out later, and we should at least try doing isometric.
Yeah,
Right.
we should try it. But I'm getting down with perspective.
Yeah. I think with isometric you don't have to foreshorten, so you're not shortening any piece of geometry. I think what you're doing is just rotating certain, like if it's not flush with the if it's not flush with the axes that you're rendering, you have to actually rotate the lines. I'm not exactly sure how you
Okay.
mathematically. Yeah. All right. So the ultimate goal for this program, which is quite long and in depth, is to draw 3 different cubes, possibly using the same geometry, the same 2 textures, right? We've got like the checkerboard texture and the F letter, and the way that they generate the F is really cool. Like there's not like a huge buffer here that's drawing an F using zeros and floating point values, right? Like they do it essentially using the 2D Canvas API.
Oh, this is gotcha. You capture it to 2D and then render it. I love it.
Yeah. And then like the cubes they have different positions and different rotations. They also seem to be shaded slightly differently, right? This one's sort of reddish, this one's sort of greenish, this one's sort of bluish. And there's a lot going on in this example. Maybe let's go I don't want to talk through too much of the perspective math stuff because we can talk about that's just going to take too long.
Okay.
But we can at least talk about what they're doing to set this all up.
Great.
Right. Okay. So if we look at the shader, the vertex shader immediately is quite complicated, and you can see that the fragment shader is it's a beast. It's got a lot going on there, right? Which maybe makes kind of some sense because there's a lot going on the surface of these cubes, right? It's not just the cube, there's some other stuff going on. But so for the vertex shader, each vertex has a big bundle of attributes. You have the position. There's no diffuse color this time. There is a normal, and there is a texture coordinate, right? Normal, again, I'm not sure why they needed normals for this. I think it's to do lighting. Lighting, you always have to calculate essentially what angle is the surface that's being hit by the ray of light so that I can basically figure how the light is being reflected.
Does each face of the cube here, like there's 4 points, but I guess there's 2 triangles for each face.
That's correct. There's 2 triangles for each face.
So in the center green F looking out,
yeah.
Is every normal pointing on that face pointing towards the camera? I guess like on the corner of the cube, are there 3 normals pointing essentially straight away from it?
So it just depends on how they set this up. So we'll have to we'll actually have to examine the data to see how they set up the normals.
Cool.
Good question.
I remembered a sphere game, by the way. Did you play Planetary Annihilation?
Annihilation. Yeah, I did not.
That's the hardest word.
Oh, this is great. It
was super cool. It was like a sequel to an old RTS.
Yeah. Nice.
But
Okay, so this could be a dope ass look for Bolo, for Manchester Bolo, right?
yeah,
This would be really fun.
what I like specifically, this one zooms out from like 2D all the way into like Google Maps. Google Maps like
Oh
3D
man,
Earth.
that's so
Yeah.
dope. Yeah.
All right.
Yeah. Well, now we've got some this is Total Annihilation, is it not?
The sequel to Total Annihilation.
Okay,
Yeah.
yes.
Anyway, that just popped into my head. So
That's great. Um okay. So here is the vertex shader again. We also have a couple of uniforms here, right? So these are sorry, go ahead.
no, I was gonna say this I recall from looking at a previous, I think the cube example on MDN too, where it's
Yeah.
every position is actually a matrix multiplication of projection and the view.
Yeah, so our vertex shader is going to map over vertices whose different have different values for the position. They're all their attributes are going to vary, but the uniforms are uniform. Right? That's why that's why those variables are named that way. Is that they're constant for at least multiple until you change them. And as you can imagine, it's actually more expensive to change uniforms than it is to like have a bunch of different vertex attributes. The whole hardware is designed to run this program over a bunch of like a big array of these structures, right? But then you kind of have to stop the whole world and like adjust the uniforms when you need those to change.
Gotcha. Oh, interesting.
All right, and then we have two outputs here. We are going to be outputting a normal and a texture coordinate and a position. So if you actually think about it, our outputs are just like essentially the inputs transformed in some way.
Yep.
Yeah. So without going into the math, the position is just going to be kind of mutated by the view and the projection. We don't actually mutate the normal by the projection because we don't care about the vertex normal being mapped into screen space. We still want the world space normal because our lighting calculation is going to happen in, I guess, world space. I guess that's the way that they're going to do it.
Okay.
So essentially, the position here, when we multiply the original position, world space position, by the view position, what we're actually trying to do is just to get it so that like everything treats the camera's position as the origin, the camera's up as the y-axis, the camera's, I guess, right as the x-axis, and the camera's like straight ahead as the negative z-axis. That's what the model view matrix is doing. It's also potentially rotating, like, or translating a sort of tree of other models around the origin of a succession of different origins. So like I have my origin as a human being at my belly button, and then my body, my torso comes off of that. But then I have two additional origins that are my shoulders, and my sort of like upper arm kind of rotates around that. And so there's like a whole succession of those things. And that all gets crunched down in user code into the model view. So it includes all the kinds of like things that are like relatively moving to their parent. Like my finger is relative to my hand is relative to my wrist is relative to my elbow. All of that gets kind of crunched down. And then, so that's the model matrix. And then there's the view matrix, which is the camera, which basically says, well, everything is like relative to the world origin, but the camera's over here and it's pointing in a different direction. And so I need to basically essentially rotate everything around the camera so that the camera is treated like the origin.
So in this case, for the 3 cubes, we'd actually be, you're saying that you would set the model uniform between rendering each cube so that you could define things in sort of relation to that.
That's exactly correct.
Okay,
so there was basically 2 ways of arriving at the thing that's being rendered into the canvas right now. One is that you just actually use completely discrete sets, discrete sets of vertices for each cube. The other is you use the same set of vertices for each cube, the same model, so to speak, and you change the uniform between them to move them, to make them seem like they're moving around.
Oh, that's clever. Okay.
Yeah. And that's probably what this program does. I actually don't know. Like I forgot. I did go through this like really quickly before, but I'm assuming that they don't actually make three completely different VAOs for this, right? Or at
That makes
least,
sense. That's a lot of
yeah.
overkill.
Yeah. Okay. So the normal, we're just doing in world space. So we're just taking the model view and multiplying by the vertex normal. We're getting normal out of that. And then the texture coordinate, we're just literally just reading it straight out. This doesn't, texture coordinates are rarely transformed, as far as I can tell. You basically, the artist sets this, or the artist pro software sets this, and you don't really need to like transform it by anything.
Cool.
If you wanted to do effects, like animating, like if you wanted to kind of like animate a texture over a surface, people do that, right? Like a marquee or something like that. You could have the shader do that for you by changing the texture coordinate. Right?
Gotcha. Okay.
The fragment shader. Oh boy. Okay, so this is kind of complicated. We have coming in from the vertex shader, or rather the rasterization phase that the vertex shader feeds. For every single pixel, we have its normal, which is again interpolated between, like, let's say this point and this point. Like essentially the normal is interpolated between those. We also have the texture coordinate that's also interpolated. And the interpolation makes the most sense to me. It's like the easiest to explain for texture coordinates, right? Like when you're drawing this point right here, you don't want either the texture coordinate at this vertex or the texture coordinate at this vertex. You want some blend of those two. Right?
That makes
the
a ton of
interpolation
sense.
makes sense.
Yeah.
Then we have a bunch of uniforms that represent the lighting and the textures, right? So essentially, when we call draw arrays, like when we actually call things, we have the shader program that's bound. We have a bunch of uniforms that we set. And among those uniforms is actually like what texture is it actually reading out of, right? Because the texture is just like essentially just like it's a GIF or it's a ping file or something like that. I don't think it's in memory, that format. It's probably just like a raw bitmap in memory or some easy lossless compression of that, right? Version of that. And those actually just get set as uniforms, right? Here's the texture I'm working on. And so if the texture needs to change, you need to change that uniform, right? We actually have two different textures. Textures in GLSL, you don't refer to textures directly. You refer to objects called samplers. The level of, like, there's essentially one layer of indirection here that I'm not 100% sure off the top of my head why that's necessary, but you can configure the sampler. I suppose there's like sampling properties that aren't necessarily part of the texture itself, but the way you're reading out of the texture. The one that comes to mind is how you deal with anti-aliasing. So if you imagine you wanted to render a texture, but do like something that emulated NES 8-bit style graphics, you'd want to do what's known as nearest neighbor sampling, which is to say, I don't want, like, if my texture is really low fidelity, it's like really, really coarse grained. It's like much smaller than the actual like geometry that's being drawn. And I'm kind of stretching the UVs over it to fit there. You may actually want to see like solid squares of color going to the next color rather than a smooth blend of color going from point to pixel. And so you do what's called nearest neighbor sampling, which is to say, like, whatever UV coordinate on the texture I'm closest to, I want exactly that color, rather than trying to linearly interpolate between the first pixel and the next one.
Gotcha. Huh.
And so that's a property of the sampler. That's like, how are you reading out of the texture? Right? So that's the uniform there. And then the other two uniforms that we set are essentially the direction of the light hitting the surface, and that's going to be if you think about that, you kind of want that to be constant for the same model, right? Or at least if you have multiple lights, you can have multiple of these uniforms. And then we also have the color of the light. So imagine that there's a light somewhere with a filter sitting over it, right? It's like a rock concert or something.
Gotcha. Okay.
And that's probably how we're getting different colors going in here, right? Yeah. So what's interesting about the canvas here, what's being drawn here, is that the lighting seems to affect the checkerboard texture. but it's not affecting the letter, right? Those like the letter F, I think basically the same color. It's kind of hard. There's a little bit of contrast there, but I don't think the lighting is affecting it, right?
Yeah, I think you're right.
Right. This is our checkerboard texture. It's really blown up, right? It's really zoomed out.
Wow.
Um,
Huh.
but this is our letter F. What I'll explain a little while why, or if we get to it, I can explain why there's a bunch of different versions of
Okay.
this. Um, but you'll notice that like there's no greenish tint on this F, and there's no bluish tint on this F, and there's no reddish tint on this F because it's already red.
Right.
So that means that the fragment shader is doing something cool. It's applying the lighting to one of the textures, but not the other. Does that make sense?
It does. I'm reading the shader. I'm curious how that's going to come out, though.
Yeah, let's talk about that. Okay, so we figure out what the vertex normal is. It's calling normalize, which basically just says that I want a magnitude of one on that. I guess that's not a service that's provided to you by the rasterization pipeline automatically. That's a little bit unusual to me because usually you want to always normalize your vectors in all this 3D math stuff, or else you get accumulate drift and that sort of thing.
Right. I would expect that the normal comes in normalized. I don't know. Search me. I guess because it's being interpolated between 2 points. If you were on a curvy surface, or if the normals were not, I guess the interpolation would not necessarily be one of magnitude
Yeah.
one.
I think they're using the word normal here to mean orthogonal to the surface,
Yeah.
rather than normalize or like standardize to one. I think they're using that sense of normal.
Gotcha. Okay.
So it's doing a lighting calculation here. We're not going to get too much into kind of like Phong shading or Gouraud shading or like lighting stuff. Suffice it to say that the intensity of the light is a function of the direction the light is going and the angle of the surface that it's hitting. That's hopefully relatively intuitive, right?
Yep.
Just by like walking around the world. And the dot product is the way that you do that. Right?
Cool. Okay.
And then it figures out the color using what is diffuse multiplier? Where do we actually use this variable light?
So not till the very end for out color. The diffuse multiplier is the red, green, blue
Okay,
tint,
yes.
right?
Yes, this is the tint, right? So it's basically saying what I would like to do is take the diffuse texture. They called this diffuse just because they wanted to apply the diffuse lighting to it. And diffuse lighting is essentially what I said is like it's just got like it's like a source at infinity that's shining a light. It's actually not. It's essentially what we experience with the sun, although strictly 100% not true, because the sun does actually emit light in angles, but it's so far away and so massive that you can almost think as the light rays is coming parallel to you on the planet Earth, and that's what diffuse lighting is essentially modeling. You can do point lighting also, which is the case where a point light actually has a bunch of different angles, like depending on where you are. And there you would have to basically take the point, you'd send the point of the light and then calculate some vector based on what point that you're actually drawing there. So the color, there's two colors that we have to care about. The color of the checkerboard thing and then whether or not we're drawing the decal over it, basically, right? So we get the color of the checkerboard by just saying, I'm going to take the diffuse sampler, which is the checkerboard. I'm going to take my texture coordinate. It's just there's a lookup table, right? And it's just going to give me a color. But then I'm going to modify that by the lighting color, by that diffuse light color that is passed in. And this is uniform. I'm basically going to shade it with a red, blue, green, or blue tint.
Okay.
Right. So then I'm going to do a completely separate thing. So this is like almost a separate paragraph of code. I'm going to basically pull out the color from this texture using the same texture coordinate, right? And I'm going to multiply that by the alpha, right? So we're going to do a little bit of a blend here.
Yeah, so it looks like the decal color becomes red or completely transparent.
Yes. So the decal color here, you can see is totally transparent outside the actual letter F, right? And so what we're getting out of this is the alpha blending does not happen automatically. We're actually literally doing the alpha blending math here. We're saying that if A is bigger, the alpha value is bigger, it's going to be this. So I think the alpha value is basically going to be 0 or 1 here.
Exactly.
It might be less than 1 but higher than 0 on the edges here. I don't know if you can tell over the stream, but it is a little bit fuzzy there.
Is it fuzzy in the render looks very sharp on the F.
Okay.
I do see the fuzz in the texture decal though.
What I actually think it is it's the, you know how I said that texture sampling,
Yeah.
you can kind of change how it's sampling it. I actually think the sampler that's being used to render this in this program currently is using not nearest neighbor, but it's using some interpolated value.
That was my guess based on the checkerboard texture too, because it's clearly just a 4x4 black and white texture that is being very strangely interpolated here.
Yes, exactly. And you'll see actually this view will update as we configure the sampler.
Oh, interesting. Okay, cool.
Which is nice.
That's
this is a really nicely made website. So what we're doing here is we're actually, like, the color of a particular pixel is going to be a blend or some choice between either the decal color or the checkerboard thing that's sort of shaded by the lighting color.
Well, yeah, and I noticed they went for they didn't want to do any blending at all. So it's color times the inverse of the alpha. So color gets set to 0 and you take the decal color, or decal color is 0 and you take the texture color.
That's exactly right. If you imagine that decal color.a can only be 0 or 1, you're essentially, without doing a conditional, you're basically doing that there. But this could be actually not 0 or 1, but in between those two numbers, and you'd get a smooth blend between the two.
Yep. It
happens to be the case that I don't know if this is true nowadays, but GPU hardware classically has not been they're vector optimized, and they are not super scalar. They do not do branch prediction. They don't. So conditionals are relatively expensive on a GPU, as opposed to your modern CPU, which is like predicting both sides of an if statement and then giving you one or the other, which has in the recent years gotten us into really hot shit. That's essentially like Meltdown Inspector is basically side channeling that exact property.
But yep. Turns out if you predict a bunch of syscalls and you weren't supposed to, you've yes. got a memory problem.
Yeah, exactly. Okay, so the output color, as you can see here, this is how we achieve this effect of having essentially no shading happening on the decal, because we're just simply not applying the diffuse color of the lighting to the decal.
Yep, exactly.
Straight up, right? And then they're basically doing a multiplication of the lighting value. This is, again, a float. So this is angle correct. I guess if we were angled away from the light, you would see this look darker. I think that might be... I can't tell if it's actually happening.
I can see, well, like, the fact that on the green cube, the top corner, you can see the distinction between the dark green checkers means that the lighting is working, because otherwise it'd be the exact same color.
Yeah, so like, yeah, exactly. This is not dark. This is darker than this right here, right? So the lighting is taking effect a little bit. Yeah. Okay. All right, so let's walk through it if we can. How much time do we have? We have. Let's take 5 or 10 more minutes.
Yeah,
is that okay?
This. Of course.
All right. There's going to be a big payoff. All right. So by the way, they have this function here called make text canvas. Mm-hmm. It's actually creating a new canvas element, pulling out the 2D context and drawing a character into
That's
it.
So
or creating the canvas. Yeah. He's even got some CSS in here. It's pretty cool.
I was gonna say this is the only way we're gonna be able to do text in the 3D context is to do
That's
this.
Exactly right.
Yep.
Yeah. Is that we got a brilliant 2D drawing package in the 2D renderer.
I love it.
Yeah. Declare our shaders here. We're gonna load up our shaders. All of this is the same, right? It's just the shaders are more complicated. You still only have one fragment shader and one vertex shader per program. We're gonna do some decluttering here. And now we're going to do a bunch of boilerplate where we pull the attribute locations and uniform locations out of the program, but structurally still the same thing that we did before.
What's the effect if you try to get uniform location or get attribute location of something that's not defined in a program? Does it throw an error, or do you just get like a -1?
That is a good question.
Okay.
I don't actually know. Well,
Yeah, not for
we
now.
would just look it up. Yeah, I mean, it's some kind of error condition that you shouldn't do or should account for.
Seems reasonable.
Okay. So it kind of looks like most of our data for our geometry is here, right? So our vertex positions, it's likely that they're going to have to get into the third dimension. So probably our positions, rather than being 2D vectors, are going to have to be 3D points. I'm guessing that it's just like every three. They didn't. It's unfortunate they didn't format this to imply what they were going for.
Yeah, if we look at I feel like looking at the vertex attribute pointer call will actually help us.
Yeah, there you go. 3 floats.
Cool.
So 3 floats per vertex. Right?
And 3 floats per normal as well.
Yes.
Okay, so that actually, and the normals answer my question a lot, which is that every vertex, every face of the cube has the same normal pointing out.
Yeah.
Totally makes sense.
So what's going to be a little bit interesting is actually this notion of vertex indices, which we haven't talked about yet. Okay.
Okay.
And this is a memory saving technique. What it is that if you think about your cube, one of the corners is actually shared by how many different triangles? It's shared by 6 triangles,
Quite a
right?
few, yeah.
2 per face. And then one corner's abutting 3 faces, right? So there's 6 different triangles that one vertex participates in. And would it be kind of wasteful to recreate the 3 coordinates of that vertex 6 different times?
Yes, indeed. That's clever. Okay.
And probably the texture coordinates are going to be the same for that vertex across every single one of those triangles. And certainly the normal you want to be the same across all 6 of those triangles. Because it's modeling the same physical point, right?
That was my question, though, because does the normal... It's the same physical point, but each face of the cube should have a different normal for that point.
That's actually an interesting point. So we'll actually let's unpack this and see where it's going. Because I could imagine that either it points directly away from the face, which is probably what you think you'd want.
That's my expectation. And it's what it looks like.
Or it points sort of like weirdly diagonally away from the center.
Away from the point. Yeah, and that feels weird. I don't think that would generate the correct lighting.
Yeah. Okay. So, well, I think one way we can look at this is like which arrays are longer. It does seem like the positions are longer, but then it's got more negatives. I almost think that they're probably the same size.
I expect they're the same.
Yeah, but when I look at the coordinates when I look at the normals, these seem like they point down the axes. So I think you're right. They point directly like on the z-axis, on the x-axis. So they're pointing like flat away from the faces. So I can't really tell based on this, but it would be interesting to see if this was ever repeated. 1, 1, -1.
Yeah.
And you may need to repeat it for exactly the reason that you just talked about, which is that, yes, it's the same position, but it's actually a different normal.
Yeah, so I think you get to... It's tough, though, because that sort of breaks down... It makes the vertex indices array much less useful, which sucks.
Yeah. Well, let's actually kind of plow through here. Vertex indices for the triangle of a cube defines 24 vertices. We need to draw 12 triangles, 2 for each side. I think that's a typo. 6 sides to a cube, 6 faces to a cube, and 2 triangles for each. Each triangle needs 3 vertices, so 12 times 3 is 36. So there's 36 entries in this array.
Okay, so that makes sense then. It's saving us 2 points per side of the cube, which are the shared points for each side. Okay.
Yeah. So that's basically implying that the vertices are not shared if they're on different faces.
Yep.
Right. So each vertex is actually each physical vertex of a cube is actually being represented by three logical vertices representing the geometry on each face. Yeah. All right. So you picked that up really quickly, which is great. So we create a new vertex array object.
3D calculus is coming back to me, man.
Yeah. Similar to before, we create the position buffer, similar to before. We bind the buffer data. We enable the vertex array objects attribute where the shader expects it to be. We specify the format of the data in that buffer and then point that VAO's attribute to that buffer, right? Yep. Do the same thing with the normals, right? It's funny that they went out of order here, but whatever. And then we do a buffer for the texture coordinate.
Honestly, that's super helpful to me that works. Okay. It's because text chord is indexed 1 in the program, so it's indexed 1 in the VAO.
Yep.
Cool. Okay.
So check this out. We're about to bind buffer using a totally different constant.
Oh, shit.
Before we were using array buffer, and now we're using element array buffer. And what this is saying is it's saying like this actually plays a totally different role than the buffers that we bounded for.
Now, it's interesting. I noticed that the element array buffer is bound on the vertex array object, not the global state.
Right.
So actually, if you were switching vertex array objects, you would also be getting different element buffers with it, which is cool.
So the element array buffer is... Well, it's being bound to the VAO that like, yeah. So there's basically only one of these things. Is that what you're saying? There's not like multiple attributes worth of it. There's only one of them.
Yeah, when it's not like going back to the global workbench. It's actually like we're diving into one of the things we've put on the table and like opening up a new compartment on that.
Yeah. So it's essentially like saying, do we want to add one more layer of indirection to the way that we're pulling the vertices out of the VAO? Or are we iterating over these things like immediately based on, just the size and the type? Or are we iterating over this thing, taking the index out of that, and then figuring out within these arrays which values to pull out, right? And this is purely about memory savings. It's all about not repeating yourself. Right. Probably at cost of some computation loss, but I'm pretty sure basically everybody does index buffers. They do this, they add an index buffer here.
Well, if it was at some point a computation loss, it's probably no longer because the GPU
does it for you.
Yeah.
I don't know if GPUs have things like cache considerations, like if you have like a level 1 or level 2 cache, where if this was maybe poorly optimized, the index buffer, you could be jumping around like your memory like dramatically. If you had a huge model, like maybe that could be a problem, but I think everybody does it like this pretty much. Yeah. But you have the option not to, right? Obviously the other examples that we created, we worked with didn't use this. Okay, so this time we have a separate location on the desk, right? We were speculating, are there two different locations of the desk that we are allowed to bind buffers to? Indeed, there are. There's the array buffer and the element array buffer, right? The element array buffer, you're right to say that like basically it is on the currently bound VAO. So what you were saying before was that like for the array buffer, it's actually sitting at the top level of state, but the element array buffer binding is actually sitting in the currently bound VAO. Sort of 6 and 1/2 dozen of the other, but like it's interesting that they represent it this way, and it makes it a lot clearer what's going on.
Yeah, strange. It's strange that to the code, this is actually completely opaque.
Yes, it's totally opaque and difficult to understand, right?
Okay.
Yeah. Okay. So this says here, this is not really needed for anything, but if we end up binding anything to element array buffer, say we were generating index geometry, we'll change cube vertex arrays element array buffer by binding null here. That won't happen. So basically what we're saying is that like, I don't want to mutate this thing anymore.
Yep.
Right. I don't want to change it anymore. And I don't want to, if I call this again, it would actually it would mutate this in a bad way.
Yeah.
And so that's why this website basically puts this binding inside this object. It's basically to represent the potential to like essentially like mutate that object in the future if you do something that isn't careful, right?
Well, and I assume that we don't bind that again. Yeah, okay. Yep.
Yeah.
God,
We essentially don't have to bind this again unless we had different models, right? If we wanted to have different models, we bind it differently, right?
Cool.
Okay. So they generate a texture, a checker texture here. What they're actually doing is just like literally creating a texture with some data in here. And you're exactly right that it's a 4x4. It's a 4 pixel by 4 pixel graphic. And they didn't have to create a GIF or import anything here because this is really easy to just generate using inline code. Let's actually bring up the texture. Where are our textures?
They don't exist yet.
They don't exist yet. Okay, because we haven't run it yet. So we're setting a bunch of texture parameters. This is basically saying how do we want to actually run sampling on this thing.
Gotcha.
I don't know why the texture didn't pop up. We did create it here.
And it's bound to the GL texture 2D. And I see the active texture as texture 0 in the global state.
I think it might have gotten hidden. Ah, it is underneath here.
Aye.
I actually kind of want to reload and I want to go back to all those texture parameter stuff because I want to see it.
Great, let's do that.
Yeah. We're going to go through this. There's no back button on this.
That seems challenging.
I just don't want to click too quickly, that's all.
Yeah, I wish you could put a breakpoint and just run to that, but... Okay, you're getting close.
And next buffer, check. Okay, creating the texture. Okay, we created a texture here.
Huh?
It has no MIPS. It's about MIP mapping. That's MIP means the actual data. I actually forget what MIP stands for, but it's when you do MIP mapping, it's when you have multiple versions of the same texture based on level of detail. Okay, so
Okay, there's a reason you can't remember what MIP mapping means.
What's that?
It's an acronym of the Latin phrase multum in parvo, meaning much in little.
Much in little, yes. Okay, so that created the texture. It's mag filter. The magnitude of the color filter is linear, so it's linearly interpolating it. Well, this is the magnification filter. I think this actually is still doing linear here. It's setting basically each of these slots to nearest neighbor. Oh, this is weird. In Chrome, I think it actually clarified these. This may be like a weird bug.
Yeah. Okay.
Yeah. And then it's saying how you want to wrap, because you can make UV values are usually from 0 to 1, I believe. Like, are you all the way to the end of the x-axis or all the way to the other end of the x-axis? But I think you can do wrapping where the UVs can actually go higher. And that's actually how you can do kind of like animation stuff, is you just like basically allow the UV to like exceed the max 1, but it'll just wrap around.
That's interesting. Okay.
Decal texture,
same shit.
Much in the same way. Yeah.
Okay, then.
Now we're actually drawing stuff.
Yep.
Okay. We have to do the viewport this time because if we're doing actually perspective projection, I think we did viewport before as well.
We did viewport, yeah.
Although it's funny because it wasn't necessary in the other examples. I don't remember them calling this in the other examples.
It's implicit with the creation of the canvas.
I see.
Yeah, so we only have to do it
why
once.
was it necessary for them to call it here?
Search me.
Okay. Uh, enable depth test, enable cull face. This stuff is all about making sure we're not drawing, like, we actually have triangles behind triangles now, right? Like the cubes are like, yeah. And we want to make sure we're not drawing like a triangle in the back in front of a triangle in the front.
I'm really excited to see what that looks like. Turn it off.
It's going to look like Assassin's Creed makeout graphics, right? We use the program. We bind the vertex array, which actually, if you recall, we unbounded
Yep.
here. You could imagine this piece starting with use program and bind vertex array in a loop in your rendering code. As you're going over different models, you want different shaders for the different models as well. You can imagine this whole thing in a loop. And then we actually have to bind our samplers to texture units. I don't know if you've ever bought graphics cards where like the marketing was like how many texture units it had.
Oh man, I've seen that, but it's been a while.
Yeah, it turns out that basically this is essentially like an IO port for reading text out of texture memory, and you have a finite amount of that bandwidth, basically. And so if you have a bunch of your GPU cores running for running different shaders, there's only so much memory you can consume, and they essentially use the abstraction or the physical representation of a texture unit to model that, right?
Interesting. Okay.
This example is kind of fun because they said like we're just going to use texture unit 6 for the checker texture, and they just didn't use 0 because 0 is the default, and they just wanted to show that you can change it. So we're saying the active texture is just texture unit 6. We're going to bind the checker texture that we created in memory to that.
Cool.
We're going to set a uniform. We got the location way above there in the code. And basically, because remember, the sampler is one of the uniforms. We have two samplers.
Right.
And then we do the decal in another one. So we have the decal here in the first unit. Wait, why is it saying decal texture?
Because that's where it got... The decal and the checkerboard both got created in 0.
Oh, they get created in 0. I see.
That's why they're doing this.
Got it. Okay. Makes sense. Then we set a uniform for lighting. So the light direction is probably going to be consistent for all 3 cubes. And then we set the uniform for the projection. The projection is not going to change, right? The camera is not changing its angle. And now we just draw the cube in the middle. Here, the model view is essentially what moves the cube around in world space.
That's cool. Yeah, so this is where we're setting... Right, so this is the model is always oriented around itself, and we move its center point. We just drag it around the world and set the diffuse.
So we're this is actually rotating it around its own origin and then moving it around the world. Cool. And that's basically what we're seeing here. So we start with the identity, we move it somewhere, and then we rotate it around that point. Okay.
Set that uniform. Set the color uniform.
Yep, we set essentially we have different colors. We have different colors for each cube, right? So we set that. Yep. And then we draw it. So bang, it's drawn.
That's cool. Okay. Yeah. All right, so we got to dig into perspective math next time, but this is awesome.
Yeah, totally. Okay, and then essentially we repeat that same thing.
Yeah, it just does the same thing with a different model transform.
Exactly.
Cool.
Now, the way that this is being drawn into the canvas is that like draw elements is almost flushing things to the screen one at a time. I'm not actually sure if that's physically what happens.
Right. I get this, like, this might be the abstraction for this thing where in fact this is not the real code that's running.
One of the big differences between Vulkan and Metal, like these lower level APIs, is that it models all of these operations as a queue, right? You have this queue and you shove everything into the queue, and you actually directly deal with the queue in your user code. Because you can imagine, like, if you literally had to tell the GPU to draw right here, that means the GPU would have to finish drawing before you like change the shader that it was working with or change the thing, right? It'd
Well,
be really slow,
and
right?
nothing gets drawn to the screen until the frame is complete. And also, like, if one cube covers the other cube, it would have done unnecessary work to draw it. So yeah, I do not expect draw elements to actually draw a pixel I could see in real time.
Yeah, at the very least, it's not flushing to the frame buffer. A
Yeah.
lot of times, basically, what's happening is we do what's called double buffering, which is that we have this buffer in the background that we kind of clutter and clear and draw on. And then we swap that with the buffer that's being used to scan out to the display device. It's basically just two pointers that get swapped.
Gotcha. So you're always right. Okay, you're always just writing to one and reading from the other.
Yeah,
but never
exactly.
never at the same time. That's
exactly.
Yeah.
But even then, I do wonder if a lot of these like uniform commands are actually what it's actually creating is like it update this uniform object, like an event object that copies, like this data into that object. And then that all gets into it. Essentially OpenGL is like creating that queue under the hood and then shipping it off to the graphics card at some point in the future. I'm not sure if draw elements represents any kind of like logical like ordering primitive for the GPU. I wonder because like this is all getting like parallelized across a bunch of different like
right. I assumed
units,
that draw elements or draw arrays that we had before actually is dropping the current world state into some vertex pipeline for the GPU to run through because our shaders need to be applied at some point.
Yep.
But I assume they get applied uniformly to every vertex once it's in the scene and not like bit by bit.
Yeah. So what actual representation is being... There's probably n levels of like layering inside the driver code in the CPU side of things. And then how that actually gets translated into the GPU is, basically there be dragons at this point.
Yep.
Yeah.
Cool.
All right. So that's our tour through various pieces of the OpenGL API. I think that probably made it a little bit clearer. I'm going to try to open this up really quickly in Chrome.
Cool.
Because I just want to make sure that
yeah
sampling.
Dude, it's amazing what a mess this screen looks like now, but like it all makes quite a bit of sense.
Where's my
is
Chrome?
Horrifying.
Yeah. Here's my Chrome.
Oh no, our secret YouTube studio.
It's really slow right now.
Too much OpenGL.
There might be too much OpenGL. In fact, this window shouldn't be drawing on top of this because this is my full screen. So who knows what's going on with it now.
Oh, that's really funny.
Oh, it doesn't help that I have my iPad open at the same time.
Oh goodness, yeah, your computer is just...
My computer is exploding right now. Oh, okay, so I'll just do it here.
Yeah.
And I want to close this entirely. Too many tabs.
I don't understand how you have two windows on the screen here at all.
Yeah, I don't really know what happened there, but all right. So draw cubes. Oh, we want yeah, it's the cubes. The cube on cube is the one where you render to a texture. It's pretty cool. We just want to get to the texture sampler piece, right?
It makes sense that it should clarify as you click through. I feel like the
texture coordinates, index buffer. All right, now we're creating the checker texture.
Okay.
Let me bump up the font size a little bit.
Oh, that's okay. We're gonna look at the image, right?
Okay. And then the image comes in. Now we're gonna set some texture parameters.
Huh?
Oh, there we go. Yes. Yeah, that's cool. So the mag filter is basically what interpolates on the X and Y axes.
As you stretch it.
Yeah, I believe the min filter interpolates between the different maps, the different scaling values. You'll see that for the text here. It did generate bitmap. What is it? Multi in parvo? Is that what it's called?
Multimin parvo. Yeah.
Multimin parvo. Many in one or Many small things and
Much in little.
much and little. Okay, so what that means is like kind of Russian dolls,
Yeah.
right? Basically, what you're saying is like when I need a very, very high definition texture, when I'm close to the object, I want to use the most high definition texture as possible. But as things go really, really far away, I may want to actually redraw the texture, like have a human redraw it so that the important details pop. Otherwise, if I just scale that one image as if I did like a Photoshop magnification on it, it might be missing it might be emphasizing the wrong things. So that's why you do a bitmap like this.
I'm surprised they did it for this auto. Like, normally you do that with a human correction. To do it for an auto-generated
Exactly.
texture seems funny, but
It seems pointless, actually.
yeah.
Yeah. What you would probably do is actually, in this case, render the text at different pixel sizes, right? Like you'd actually literally render it at different pixel sizes and have the 2D render, because the 2D render would figure out what to
Yep.
like. It's much better in Photoshop, for example, to like change the point size of your text rather than just like draw your text, commit it, like flatten it to the image, and then just like rescale it. Like,
Right, because a human actually corrected for different sizes already.
yeah, or the font or the text rendering engine knows how to render the smaller text. You know, it knows in the anti-aliasing and all that kind of thing what things to emphasize. And so that's why we have this concept of maps and level of detail, essentially. Like what things do we want to emphasize?
Interesting.
And these are obviously powers of two, or they're not obviously powers of two sides, but they're obviously very different sizes. And so if you're some distance away, if you're like halfway the distance between what would be shown, the distance like when you would show this texture and this texture, you need some way of interpolating between those two. And that's what the min filter is for. It's basically
Gotcha.
saying, I'm going to basically like kind of like use half of one and half of the other and blend them. Right.
Neat.
Yeah. Cool. I'm glad that this actually clarified itself, because I was like, oh, wait a minute. That's not showing the nearest neighbor filtering here. Yeah.
Man, that's cool.
Yep.
Whew.
All right. We are way past time. Thank
We're
you
a
for
little
hanging
over.
on.
Yeah. No, I mean, I wanted to see that example through. I think we should try some perspective stuff next week and really get our
Okay. Yeah,
Get
I'd be
our
totally
cubes going.
down for that. Perspective math is actually simple in concept, but then when it gets thrown into matrices, it just seems like a hot mess.
Yeah. I saw what they wrote down. I look forward to trying to figure it out on my own.
Yes.
All right, sweet. Well, I will hit the stop Twitch button. Goodbye, Twitch.
Good night, everybody.